What's up, gang? It's Rahman. Today we're gonna talk about conservation of rotational kinetic energy. Bang bang, bang bang.
Firstly, we're going to talk about rotational kinetic energy, which is the energy associated with the motion of spinning. Let's check it out. If you remember, if you had linear speed, which is v, you had kinetic energy. There's going to be two types of kinetic energy, so we're going to specify that this is linear kinetic energy. You're used to this equation KL equal to half mv squared. I put a little L there to indicate this is the linear type of kinetic energy. That's because now we have a new one, which is if you have rotational speed, instead of V is W or omega. You have rotational kinetic energy, and instead of KL, we call it KR. Now the equation is very similar. It's half. Instead of using M, we're going to use the rotational equivalent of m, which is I, moment of inertia. Moment of inertia is the name given to rotational inertia, the rotational analog of mass for linear motion. It appears in the relationship for dynamics of rotational motion. The moment of inertia must be specified with respect to chosen axis of rotation. For a point mass, the moment of inertia is just the mass times the square of perpendicular distance to the rotational axis, I equal to mr squared. That point mass relationship becomes the basis for all other moments of inertia, since any objects can be built up from a collection of point masses. And instead of v, we're going to use the rotational equivalent of v, which is omega. So I get this. So if you remember the first equation, it should be easy to remember the second one. On a special case, there's a special situation when you're moving and rotating, so you have a v and a omega. This is calling rolling motion. One of example of this is if you have a toilet paper roll that is short of moving this way while rolling around itself. It's a toilet paper that rolling on the floor. It has both kinds of kinetic energy. I'm going to say that the K total is KL plus KR.
I used to spin the ball just like that. You see that? See that circle right there on top of the ball? Same thing. Now what you try to do is spin the ball straight and find the middle of the ball, just like so. See that? It's the middle of the ball right there. That's as you was on top, just like that, as you saw before. Try to balance it, just like that.
one of the applications for conservation of rotational kinetic energy, which is a flywheel. A flywheel is a mechanical device specifically designed to efficiently store rotational energy. Flywheels resist change in rotational speed by their moment of inertia. The amount of energy stored in a flywheel is proportional to the square of its rotational speed. The way to change a flywheel's stored energy is by increasing or decreasing its rotational speed by applying a torque aligned with its axis of symmetry. Common uses of a flywheel include smoothing the power output of an energy source. For example, flywheels are used in reciprocating engines because the active torque from the individual pistons is intermittent. Next, energy storage system. Next, delivering energy at rates beyond the ability of an energy source. This is achieved by collecting energy in a flywheel over time and then releasing it quickly at rates that exceed the abilities of the energy source. Lastly, controlling the orientation of a mechanical system, gyroscope and reaction wheel. Flywheels are typically made of steel and rotate on conventional bearings. These are generally limited to a maximum revolution rate of a few thousand RPM. High energy density flywheels can be made of carbon fiber composites and employ magnetic bearings, enabling them to revolve at speeds up to 60,000 RPM. Assalamualaikum and hi guys. Now let's apply the ideas of rotational kinetic energy. Let's look at a generally problem-solving strategies for rotational kinetic energy. So guys, we can say that rotational motion is motion about a fixed axis. As the rigid body rotates, all points on the body move in circular path. For example, calculating helicopter energies. A typical small rescue helicopter has 4 blades. Each is 4 meters long and has a mass of 50 kg. The blades can be approximated as thin rods that rotate about one end of an axis perpendicular to their length. The helicopter has a total loaded mass of 1000 kg. A. Calculate the rotational kinetic energy in the blades when they rotate at 300 rpm. B. Calculate the translational kinetic energy of the helicopter when it flies at 20 meters per second and compare it with the rotational energy in the blades. So, the strategy for this question is rotational and translational kinetic energies can be calculated from their definitions. So, the wording of the problem gives all the necessary constants to evaluate the expressions for the rotational and translational kinetic energies. So, the solution for this question, first thing, the rotational kinetic energy is K equal to 1 over 2 I omega square. So, using the equation, so we must convert the angular velocity to radians per second and calculate the moment of inertia before we can find K. So, the angular velocity omega is omega equal to bracket 300 ReV over 1 minute, bracket again 2 pi radian over 1 ReV, bracket and bracket again 1 minute over 60 seconds, bracket and equal to 31.4 radian per second. So, the moment inertia of one blade is that of a thin rod rotated about its end. So, the total I is 4 times this moment of inertia. It's because there are 4 blades. Thus, I equal to 4 mi square over 3 equal to 4 open bracket 50 kg close bracket open bracket again 4 meter close bracket square and over 3. So, what's the answer? Grab your calculator now. So, the answer is 1067 kg meter square. So, next, entering omega and I into the expression for rotational kinetic energy give K equal to 0.5 open bracket 1067 kg meter square close bracket and open bracket again 31.4 rad per second close bracket square, and you should grab your calculator now to know the answer. So the answer is 5.26 times 10 the power of 5 joule. So next, for B, entering the given values into the equation for translational kinetic energy. So we obtain that using the equation K equal to 1 over 2 mv square equal to open bracket 0.5 close bracket and open bracket 1000 kg close bracket and times 20 meter per second in bracket square. So the answer is 2 times 10 to the power of 5 joule. To compare kinetic energies, we take the ratio of translational kinetic energy to rotational kinetic energy. This ratio is 2.00 times 10 power of 5 joule over 5.26 times 10 to the power of 5 joules. So the answer is 0.380. So the significance is the ratio of translational energy to rotational kinetic energy is only 0.380. This ratio tells us that most of the kinetic energy of the helicopter is in its spinning blades.